Hello peeps, let's do a little work in electric fields. Okay, so probably one of the harder concepts to understand is what's called potential, electric potential, and how charges can move. And again, you and I can't move them. These are electric fields can make charges move. You see that opposites attract, likes repel, they can push, they can attract, that's how we can move them. So I start with these two sample charges, two sets. In case A, I say there's a negative 10 coulombs, which again are ridiculously large amounts. This is just for demonstration purpose. And this is a positive one. Case B, I have negative 20. So first of all, would they attract or repel? They would attract because they're opposites, duh. But in which case, would the force be a stronger attraction? Clearly, this one has more charge. If you think about Coulomb's law and we were to figure out the force, it would be a lot more. When we have charges separated like this, we call it a difference of potential, okay? It's a difference of charge, but we refer to it as called potential. And in order to move these, let's say these were fixed and I couldn't move them. They were on some kind of constrained area. And these were smaller and able to be moved. This one would take more work to move because there's more charge involved. This has a higher difference of potential. It would require more work to move the charge. This one attracts with the lesser force. This would be easier to move away, even though they're attracting. And the work to move them, okay, it has to do with how much force. So in both cases, we just have a little statement here, they're attractive. And B, more work would be required to move it, the Q, because the attractive force is greater. So the amount of work to move a charge is called potential difference or voltage. It's actually measured in voltage. Voltage is a unit. The actual formula looks like this. V equals W over Q. But I cross multiply it just to make an easier formula out of it. And we have work is the potential difference times the charge. Now potential difference is measured in voltage, capital V for volts, named after a guy named Volta. Work is still measured in joules, just like when we did energy, and Q, which is charge, is in coulombs. And I tend to use this as a small q because we talk about moving charge, so we wouldn't be moving large charges. So where do we see difference of potential? We see batteries. So let's take a look at this little battery right here. This is a AAA. I'm gonna zoom in. And hopefully you can see 1.5 volts. How about a AA? It's bigger, right? Let's put it here. Let's find there. Oh, there's AA. Oh, look at that. 1.5 volts. How about a C battery? Let's find it. There's C. Oh, look at that, 1.5 volts. Let's go with the big D battery here. Oh, there's a D, and look, 1.5 volts. So all of these batteries that I just showed you that are all different sizes, they have chemicals in them. And they have plus side and a minus side, right? You guys all know minus and plus. There's chemicals separated and they have charge. Even though they're all different size and they have different amounts of chemicals, they have the same difference. They're all the same 1.5. Now, I can bring in this guy. You guys have seen these, right? That's a 9 volt. Yet, it's not terribly small compared to like the D or the C. It has chemicals in it. It has a different amount of chemicals to make a difference of potential that's greater. And then you find these little guys, right? You see button batteries all the time. This one is 3 volts. It's tiny compared to these. Okay, you can see it's very flat. Again, it's about the chemicals in there and the difference between the positive and the negatives that store up what we call potential difference. That's what batteries are. So they're an example, and when you hook up a battery, well, that's the next unit. We get into moving charges. For right now, we think about them as being static. All right, so batteries are a good example of where we would have charges that we would want to move. All right, so let's start with the first example here. It's a fairly quick and easy formula. How much work is done moving 2, I don't really need an X there, it should be just 2 microcoulombs in a potential difference of 10 volts. Okay, so work is my unknown. This is my charge, and a potential difference is the V. I know V gets V. So work equals VQ. So work equals 10. And remember, micro is 10 to the negative 6. So 2 times 10 to the negative 6. Now, multiplying by 10 just means to move the decimal once. So it equals 2 times 10 to the negative 5th joules. Pretty simple. All right, example 2. How much work is done to move 1 electron in a potential difference? Okay, so work, 1 electron, that's the charge. And you have to remember that that is 1.6 times 10 to the negative 19th coulombs. Remember, I'm not putting the negative in here. And this is my voltage. So W equals VQ. So we're going to have 1,000 times 1.6 times 10 to the negative 19. Now that's just going to move my decimal 3 places, so that's going to be 1.6 10 to the negative 16th joules. All right, so there's a lot of scientists who do work with these kinds of energies, moving small charges, and decided to come up with a different energy unit because this is a lot to use. So instead of using the actual charge, because it's usually electrons that we're talking about, that they're moving because they're available, they came up with a different way to do this. They said, let's just, instead of using the actual charge, let's just put in how many electrons and come up with a new unit. Sometimes units are made for convenience. For example, when we measure the distances to stars, we don't typically use meters or even miles. We use light years. Well, a light year is the distance the light travels in 1 year. Why? It's a convenient unit. Because stars are so far away, it's easier to use light years because then I have smaller numbers than I have to use, than using like billions and billions and billions of miles. The same thing happens with something called the astronomical unit. We use it in the solar system. Earth is 1 AU from the sun. So it's not that nobody's ever come up with a convenience unit. This is a unit of energy kind of brought about for convenience. So instead of putting the actual charge, we put in the unit, the number, hashtag, I know, number sign. So in this same, just repeating this, it would be W equals VQ. We would still have the 1,000 volts, but instead of 1 electron's charge, we would just put 1 electron. That's a lot easier to multiply, isn't it? Okay, that is going to equal to 1,000, and the new unit is called an electron volt. It is an equivalent energy, so if you do the math, 1,000 EVs equals 1.6, but it basically turns into this number, and you would need to highlight. So yeah, there's that number once again, 1.6. That's because it's the charge of the electron. So electron volts are not a potential difference. They are an energy, and it's the energy associated with moving charges through electric fields. Electric fields are what makes electricity go. We're still on static. We're not moving it yet. That's next unit. All right, so you're going to do some practice with this today. You have a worksheet. Bye.